So what we just saw in the previous lecture is this really important idea. Here's the root. This is just the picture that we saw at the end of the previous lecture. We start at even, we go to odd, we go to even. We can branch at even. We can never branch at odd. So we might have a situation like this. And again, the key point is that these highlighted edges we cannot explore. The M alternating tree cannot add these, and you can see here that possibly this could be problematic in the sense that our tree might stop growing, and we haven't reached the end. And so this was called the blossom. We labeled this B, and the graph G mod B, if you want to call it that, would now look like R, which is even. Anything that is not in the equivalence class, of course, is not affected by this operation. Here's E. And now I have my two yellow edges and the other edges. So I'll just highlight these again just to make it clear that now we are allowed to add, if we're growing now the tree, I can now add these edges. So what do we need to check? We need to make sure that I've done this operation. I need to make sure, what are we trying to do? We're trying to, we need to show that if there was an augmenting path before, I haven't ruined the augmenting path. And so this is the first thing that we want to show. So let me write this informally, and then I'll write the lemma. So I need to show that contracting the blossom preserves any M augmenting path that I had, and I'll state this in the following way. Let this denote the contracted graph, and similarly I can use this to denote the contracted matching. You can see just from the illustration that there were two edges in the matching that now got pulled into B. So this lemma says that there exists an M augmenting path in G if and only if there exists an M mod B augmenting path in the contracted graph. So this tells us that I can continue this procedure, and what is going to happen? I contract a blossom every time I have an even to even edge. So at least the intuition here is that we're going to continue contracting blossoms, and one of two things can happen. First, I find an augmenting path, and in that case, this lemma says that I'll find an augmenting path at some point where I may have contracted several blossoms, but this lemma says that if there exists an augmenting path in the contracted graph, there exists an augmenting path in the original graph. And then the other thing that can happen is that I don't find an augmenting path, and I can't contract any more blossoms. But now we're going to be back in the realm of the lemma that we proved, the sufficiency lemma for optimality, because it means that we'll have terminated our procedure, we will have failed to find an augmenting path, and we're unable to do any more contractions, but that of course means that there are no even to even edges. That will tell us that the lemma applies to our contracted graph, and therefore in that contracted graph there are no augmenting paths. But that is exactly the contrapositive of the statement of the statement that if there exists an augmenting path in G, there has to exist an augmenting path in the contracted graph. In other words, if there are, by the lemma, no augmenting paths in the contracted graph, sorry, if there are no augmenting paths in the contracted graph that has no even to even edges, then what this lemma tells us is that then there are therefore no augmenting paths in G. And that is the story. So now let's fill in the details of this lemma and then pull it all together and make sure we understand how this implies that we have an algorithm. Okay, so again, we want to show that there exists an augmenting path in G if and only if there exists an augmenting path in the contracted graph. Okay, so let's do this direction. So in other words, I want to show if there's an augmenting path in the contracted graph, then I can find an augmenting path in G. And again, this, we need obviously several details. You see, it's going to take us 3 slides to get through this. But the idea is all comes down to that picture we saw in the previous lecture, and this idea that contracting the blossom changes parity, or in fact just removes any issues I have from the parity of having to make that decision of trying to make an augmenting path going one way around the odd cycle or the other way around the odd cycle. Okay, so let's suppose there exists an augmenting path in the contracted graph, and if this augmenting path doesn't go through the blossom, then obviously then the result is trivial because it's exactly the same. I can identify uniquely the edges in the contracted graph and the non-contracted graph. So let's suppose that the augmenting path goes through B. Otherwise, we're done. And so what are we going to do? In order to create an augmenting path, an M augmenting path in the graph, we're going to follow this until we get to B. It's kind of obvious. Okay, so now the question is, what are we going to do now? Well, it's exactly the intuition of it's exactly the intuition from the picture. So then we continue in one direction or the other. So in other words, here is my augmenting path in it starts from an exposed vertex. And this corresponds to my collapsed, let me make it bigger. Oops. Here's my node. I'm making it on purpose big so that you can see that it corresponds to my collapsed I'm really just drawing the picture from before, but now I'm drawing the augmenting path. Okay, so here we are. This is in the contracted graph. This is an example. And I have found an augmenting path, namely yellow is, I'm switching around the colors on you, but okay, let me not do that then. I add this edge. The augmenting path is this color. And so here is my augmenting. Here is, I'm sorry, don't know how I deleted that other edge. And so this was, apologies. Here, what are we doing? Right. So the two edges that are, the two squiggly edges in the darker color are the previous matching, contracted matching. And then in the lighter color, I found my augmenting path. And my point here is that I can now find an augmenting path in the bigger graph, because what happens? So let me now draw what the expanded graph looks like, or might look like. And you see what happens here. First of all, note that we could, so note what happens. I add this edge. And then, as I'm making my augmenting path, when I get to the blossom, I just have to make sure that the parity works out so that once I get to this node, I can add this edge and this edge. So that means that in order to add this edge, what do I have to do? I have to go down the path below, because I need to alternate even, odd, even, odd, even, odd, even, odd. Whereas you can see that if I went over the top, I would not have the right parity. Even, I'll choose yet another color. I would have even, odd, even, odd, even, and then I would run into trouble there. So the simple intuition here is that we can expand, we can turn an augmenting path that goes through a blossom in the contracted graph into an augmenting path in the full graph, just by virtue of the fact that a blossom, by definition, is an odd cycle. And therefore, I can guarantee that this path will work out because I'll go through the odd cycle in one direction or the other, and therefore the parity will work out. So that is the key idea. Okay, so now so what have we seen? We've seen that if there's an augmenting path in the contracted graph, there is an augmenting path in the uncontracted graph. So now I want to show the other direction, that if there's an augmenting path in the graph G, then I do not destroy the existence of an augmenting path by doing any of these contractions. And that is equally important. So, and note that it's equivalent to prove the contrapositive. So it's equivalent to show that to show that if there exists an augmenting path in G, there exists an augmenting path in G mod B, is the same as saying that there is no augmenting path in G mod B implies there is no augmenting path in G. But also I can show that M is there is no augmenting path is the same as writing that is that we're not maximum size. So it's equivalent to show that M is not maximum size implies that the contracted matching is not maximum size. So this is equivalent. So we're going to show this. I'm going to show this implication. Okay, so let's go back to what our blossom looks like. again, this is our picture. We've got our stem and then our blossom. So this, as we've mentioned, this branching can only happen at an even node. Right? Odd nodes are always extended by the matching. And that means that if there's a branching, it has to be an even node, which means that this must be, what we call the stem is odd length. It has to be, because we go even, odd, even. You start from E, you end in E, you're going to be some even number. In this case, it's 3. So if it's an odd number of nodes, it's an even number of edges, and therefore I can just swap what is in the matching and not in the matching. So I can always redraw this. Now this is not how I would draw a tree. All right, once you give me this maximal tree and I have this blossom, I can do this procedure. I can always make this look like this. Note that I have not violated any property here. I don't have matching attaching to a matching. So this is the picture in M. I'm going to make a new matching, which I'll call M dash. That looks like this. I've just swapped the edges. So I'm going to swap edges in and out of the matching in the stem. And again, because the stem is odd length, this is not change the size of M dash. So in other words, M dash is equal to M since stem is odd length. In symbols, if I call this stem S, what I've really written is M dash is just the symmetric difference of M and S. Okay, so what has this accomplished? What this has accomplished is that now the exposed vertex is now in the blossom. Okay? This is the main thing that I wanted to accomplish. So this is exposed, whereas initially I had R, which was exposed. Okay, so now I want. So now what do we have? If M is not maximum size, as we mentioned, this implies that M dash is not maximum size. And by our characterization of maximum matching from 2 lectures ago, that means that there exists an augmenting path in M dash. Okay? So we're going to use that augmenting path to find an augmenting path in the contracted graph, which is exactly going to imply that there is an augmenting path. There is an M mod B augmenting path. So by assumption of M not maximum, it implies that M dash is not maximum. Hence, there exists an M dash augmenting path, and let's give that a name. I'm going to call that Q. So what are my possibilities? The easy case is that Q doesn't touch the blossom. But if Q doesn't touch the blossom, then I can do the reverse procedure that I did in the other direction, and then I can convert Q into an augmenting path in the contracted blossom. So we're done in this case. So the only interesting case is that actually Q does touch the blossom. Okay, so what does that mean? remember that our graph now and the matching m prime, we've got our root, and I've changed it by our swap of the stem. The root is now not exposed anymore, and we have this situation. And so this is our exposed vertex. And also by assumption, in our blossom now has only one exposed vertex. Initially, a blossom has no exposed vertices, but our blossom has only one exposed vertex. So since Q is an augmenting path, it has to go from an exposed vertex to an exposed vertex. So therefore, it's got to start. It might go. It has to start somewhere over here. So it has to go something like this. I don't know what it does exactly, but it has to start at Q starts at some other exposed vertex that has to be not in the blossom, because the blossom only has one exposed vertex, and we already know that that one exposed vertex is there because we created it. So the claim is that is as follows. The claim is that Q is we can make it m-b augmenting in the contracted graph. And so let's see why this is true. So indeed, in the contracted graph, the entire blossom, this is B, the entire blossom B corresponds to a single node, and it has to be exposed to a single vertex which must be exposed. And so in other words, how do we know this? We know this because if we look at our original blossom, it could only have edges. It has edges that look like this, but you can see that none of the edges coming out of the blossom are ever going to be matched. They're always going to be unmatched. So that means that once I contract this blossom, this is a picture that we've now seen many times, even with the swap of the stem, what it's going to look like is our old root, which is now matched, an unmatched edge, and this is our supernode, which is now the blossom, and then it, continues somehow to some other node. And you can see that it goes unmatched edge to unmatched edge no matter what path it takes. So the entire blossom corresponds to an unmatched edge. And that is pretty much the story, because let me draw this actually again down here. Sorry for drawing it in multiple places here. So in G mod B, what does this look like? The root, now matched, again because of our swap, now unmatched. This is B. I don't know what edge it takes, but it's certainly unmatched. And then this node here that I drew is somewhere out here. Starts as unmatched, then it goes matched, and then again I don't know what it does, but at some point it must have been taking one of these unmatched edges, because that's all that is touching B. And therefore that means that this is also an augmenting path. So this is also a m-b augmenting path in G mod B. And so again, the key point is that all of the edges leaving B, leaving any node in the blossom, have to be unmatched. And so no matter what you do to get to this node, no matter how that edge was, how that path Q was coming in, it was arriving at some point of the blossom. I don't care which of the nodes on the odd cycle. It was arriving at some node in the odd blossom through an unmatched edge. And therefore, because Q is augmenting in the uncontracted graph, then Q mod B is Q mod B is augmenting in the contracted node. Again, the whole point is that B remains exposed, and that basically concludes this key result. Concludes this lemma. Okay, so what have we learned so far? We're basically ready to put this together into Edmonds' algorithm. We've learned that if we are growing these alternating trees and we terminate and we have no even to even path, then we're optimal. And we've also learned that whenever we do have an even to even path, if we contract it, we are not creating or destroying augmenting paths. So this suggests an algorithm, and this is Edmonds' algorithm, and it goes as follows. We construct maximal M alternating trees. If and in this process, by saying we construct M alternating trees, of course I mean of course I include that if we find an augmenting path, we add it and stop and repeat. So I'm assuming we don't do that. So if there exists an even to even edge, contract the blossom and continue. And actually, I should have written that if there doesn't exist that, if there does not exist an even to even edge, then M is maximum by the previous by the lemma that we showed, that we stated at, and proved in the previous lecture. So if there does exist an even to even edge, then we contract the blossom and we continue. And if there exists an augmenting path at any stage, so let's just say in G after contracting blossom B1, and I'll use this notation, contracting blossom B2. Actually, I'll just leave out these parentheses and write in this way. So this just means I contracted blossom B1, then B2, then B3, and I continue contracting, say, some finite number of times. So if I ever find an augmenting path in the contracted stage, then with the procedure described essentially in the constructive proof of the previous lemma, we find the corresponding augmenting in G. And finally, if there is no augmenting path and no more, because we contracted them all, even to even edges, then we stop. So we need to do two things. We need to check that we need to have a proof of correctness, that if it terminates, this has either certified that M is optimal, or it's basically that if it terminates, it certifies that M is optimal. And then we also need to check that this terminates in polynomial time. But these are both fairly straightforward. But let me nevertheless write it as a theorem because it's important. If the algorithm terminates, then M is maximal. So this is basically putting together the two lemmas that we've proved. So when it terminates, when the algorithm terminates, the current matching in whatever the contracted graph happens to be, in G, with the K contractions is maximum size. Why? Because there are no even-to-even edges. This is our sufficiency lemma. Sufficiency lemma. But this implies that there does not exist an augmenting path anywhere in G in this contracted graph, which also implies that there does not exist an augmenting path in G by the previous lemma. And that shows that if this terminates, then indeed we have to be optimal. And then just a simple check to wrap up the last details. Let's make sure that that we have polynomial time termination. So what does this algorithm require us to do? Clearly, building M alternating trees is certainly a polytime operation. We just keep adding. So we don't need to do anything more than just scanning the edges and the vertices. And now what happens? When does that process stop or have to restart? And it does so in for one of two reasons. Either because we find an M augmenting path, in which case we restart the whole process, or because we contract a blossom. So how many blossoms can we contract? So we can, and the answer is clearly not that many. We can contract at most, obviously this is way more, because every time you contract a blossom, you subtract a constant fraction of nodes. So we can contract at most order V blossoms before either terminating with a maximal tree that has no E to E edges, no even to even edges, or before, in which case we're optimal when we terminate the whole thing, or before finding an augmenting path. And finally, the matching, how many times can it be augmented? It can only be augmented order V times. The matching can be augmented at most V times. In fact, V over 2 if you start with just the empty matching. So that is the story. And this shows that we have an efficient polynomial time algorithm for finding a maximum size matching in a general graph. Our next step from here is going to be to study the polytope of maximum matchings and of perfect matchings, and to understand the polyhedral structure of that, similarly to what we did when we looked at the R arborescence problem. And we're going to find that it's a polytope that that has exponential number of facets, and so we're gonna tackle this and integrality of that description in the next lectures. We'll pick it up then.